Video 1 of Chapter 7. We are going to be discussing this idea that's really going to recur throughout the entire semester, and that idea is of a sampling distribution. So in today's video, we will discuss the main ideas behind what is a sampling distribution and how does one create a sampling distribution, and what are some of the main ideas in a sampling distribution. Now, so far in AP Statistics, there are 4 main themes, and we've discussed 3 of them in first semester, and that was describing data, producing data, and probability. All of second semester of AP Statistics revolves around this idea of inference. And you might be asking yourself, what is inference? Well, I'm glad you asked. That's when we get to make or test a claim about a population. We might ask ourselves, what percent of voters will vote for candidate A in the next election? Or what is the average life expectancy for US residents? We can test certain claims about what we might think is true about the percent of voters, or we might take a sample of voters and use that sample to estimate what percentage of voters would vote for candidate A. Now, questioning everyone in the population, which is called a census, would just take way too much time and money, so we'll settle for the next best thing, and that is to take a sample, preferably a simple random sample, from the population. Now, we could take other different kinds of samples, as we've mentioned previously in Chapter 4, but the main thing we're going to be looking for is a random sample of some kind. Now, since we don't know much of anything about our population distribution, for example, its size, its shape, if it has any outliers, what its center is, and what its spread is, then we need to rely on a distribution called the sampling distribution. Now, the sampling distribution will be based on, get this, I know this is hard to believe, but a sampling distribution is based on a sample, and a population distribution is based on the population. Since we can't get around to asking everybody in the population, we really have no idea what the center and the spread of the population is, or if the shape is maybe approximately normal, so that we can do some nice calculations with it. But this sampling distribution, we will be able to know some nice information about it. So the first question is, what is a sampling distribution? Well, by definition, a sampling distribution is if we took every possible sample of the same size from the entire population and graphed the statistics, and by statistics we mean, like the sample mean or the sample proportion. If we were to graph the stats of all of the samples we gathered as a dot plot or a histogram or somehow to display this data, then that is what we would call the true sampling distribution. Okay, the true sampling distribution is when it involves taking every possible sample of the same size from the population. Now, to be honest with you, the true sampling distribution is just about nearly impossible to obtain because the populations we're going to be dealing with are just way, way too big. So even though we don't get to see the true sampling distribution, just even seeing a small snapshot of a sampling distribution will give us enough information to make some pretty good estimated guesses. Now, what if I wanted to see how many, let me rephrase this, how many different samples of 10 people would we have to gather to cover every possible sample from just a population of size 2,000? Well, there's really only whatever that number is. And to put that in perspective, a Rubik's Cube has 43, I'm trying to think, this was millions, billions, trillions, quadrillions, quintillions, 43 quintillion different configurations. And this has way more than that. Okay, so again, this represents the true sampling distribution. And we're not going to have enough time to take that many combinations of our population. So, thankfully, we don't need that many samples to make an educated decision about our population of interest. The main thing we need is just one big enough sample. But you might ask, how big, Tom Hanks? I don't know. You guys even know what the movie Big is anymore? Because I bet you don't. You guys are like, I don't know, too young of kids to know who. You probably don't even know who Tom Hanks is anymore. He's Woody from Toy Story, but he doesn't really look like Woody in real life. I'm sorry, that's just a cartoon. How big of a sample size do we need? Well, it really depends. It depends on some factors, and those are factors that we will discuss throughout this chapter. So what is so special about a sampling distribution? Well, the sampling distribution gives us valuable information in these socks. It tells us the shape, it tells us the center, it tells us the spread, so that we can try to calculate some probabilities, um, hopefully using some normal distribution calculations. Now, there may be only one population distribution because there's only one population of interest, but there are as many different sampling distributions as there are people in the population. Because earlier, when I told you the definition of a sampling distribution, I said it's if we took every possible sample of the same size. All right. And so in this example, I said, what if we did samples of size 10 from a population of 2,000? Well, I could make a different sampling distribution if I had taken samples of size 11. And I'd have a different sampling distribution if I'd had samples of size 12 and of 13 and of 14. So really, there's many sampling distributions. Now, we're going to explore some patterns that emerge from sampling distributions depending on the sample size taken. So here's the main idea we're going to be looking at this video. We're going to let this represent the population distribution of a die. And this represents me rolling a single six-sided die. Okay, here are my outcomes, 1 through 6, and this is the probability of obtaining those numbers. So we can see right now, based on the population distribution, I could actually figure out the center and spread and the shape being uniform. The center, if I were to use some ideas from chapter 6 when we did discrete random variables, I know that the mean will be 3.5 and the standard deviation will be 1.708. So I wanted to give an example of where we knew the socks of the population. So this is our starting off point here. This is what we know about the population. But now let's say for our first sampling distribution that I roll a die twice. So I'm looking at sample sizes of 2 here, and I calculate the mean, and I graph the mean, and then repeat rolling that die twice 499 more times. Okay? So again, how many times could I theoretically roll a die twice and calculate a mean? Well, really there is no population size of a die. So, I mean, I could be doing this till the day I die, and the day you die, and the day your grandkids die, and this video is just getting really depressing talking about all this stuff. Anyway, if I were to look at this new sampling distribution, I can tell the shape is no longer uniform, but it's starting to have this bell-shaped curve to it. So I might call it roughly symmetric or approximately normal-ish. But if I were to calculate the mean roll of 2 dice out of 500 total trials, the mean is 3.46, which is pretty darn close to the population mean of 3.5, right? Just a little bit lower. Now the standard deviation, if you notice, if the mean is still right around here, around 3.5, I have fewer outcomes out here on my tails, which means my standard deviation is going to decrease. And it decreased by about half. We were at 1.708 in the population. Now we're at 1.2349 in our first sampling distribution here. What if we were to look at a second distribution, sampling distribution? What if I rolled the die 5 times, and then I calculated the mean of those 5 rolls, graphed that mean, and then again repeated 499 more times? Okay, so just in case you're kind of having trouble digesting what this graph is telling you, this right here, this 1.2, I'm going to gather here that this probably only happened one time out of 500 total trials. And to get a mean of 1.2 meant that I had to roll a die, had to roll a 1 4 times, and then on the 5th time, I rolled a 2. Okay? So how often are you going to get 4 1s and a 2? Not necessarily in that order. Not that often. Same thing down here on this end. Look at this 5.8. I'm going to gather that's probably worth 1. That only happened one time. Well, that's me rolling a 6 4 times and then a 5. And how often does that happen? Not too often, right? For the most part, we're going to roll numbers that are, scattered across here. And if I roll some small numbers and some big numbers, they're going to average out to be somewhere in the middle. And that's where most of my observations are happening. Now, with this second sampling distribution, I still see that kind of rough bell shape to it, right? So the thing I notice, it looks more approximately normal, right? It's definitely looking more bell-shape-ish. the mean of this sampling distribution is still right around 3.5 like the population was. But I notice the standard deviation keeps shrinking. Okay, it was 1 point, what do we say, 2349 in this sampling distribution, but in this sampling distribution, it decreased by just about another zero point 0.5. So it keeps getting smaller and smaller. And one more example, what if I were to roll that same die 10 times and then calculate the mean roll for those 10, graph that mean, and then do it 499 more times? Well, if we look now, uh, in this case of a 1, we see that it didn't happen at all. But what does this 1 really mean to the sampling distribution? That would have meant that I had to roll 10 ones, and the average of 10 ones is 1. And I can see that never happened. And really the first thing I see that happens is, what are we at here? About 1.95 maybe? Which means I had to roll quite a few ones out of those 10 rolls. But then I also had some bigger ones, like maybe some 2s and 3s mixed in there. We can see on the opposite end that we didn't roll 10 sixes in a row, not even 9 sixes in a row. But something happened where we got a lot of high numbers, okay, but there were still some small numbers in there. Now, the main thing I want you to see about the shape as we went from the population distribution to the sampling distributions was that the shape was starting to turn more and more and more of an approximately normal distribution. Even though the population was not normal, I mean, this was anything but normal, this was exactly uniform, the sampling distribution started to turn into a normal distribution. Okay? And you got to notice as our sample size increased from when I rolled the die 2 times to 5 times to 10 times, it starts to look more and more and more like a true normal distribution. Yes, there's some jaggedy edges in here, but if you notice, this definitely looks much more bell-shaped than it did with sample size of 2. Um, to put it into another perspective, the larger the sample size, the more idea you have of what the true shape is going to be. I kind of think about this sampling distribution being like a regular Nintendo, maybe this sampling distribution more like a Nintendo 64, and then you get into like the Wii and the Wii U, and man, you get to see so much clearer when you have much more bits of processing going on. The center. What we noticed about the center was it really didn't budge a whole lot, right? The population mean was 3.5, and all of our sampling distribution means stayed around 3.5. Now, were they exactly 3.5 every time? No. Were they really, really close to 3.5? Yes. And that'll be really the main idea that we're going to look about the centers of sampling distributions. Is it really the centers of our sampling distributions are really about the same as the population center? So even if we didn't know what the population mean was, okay, even if, let's say, we didn't know that this was really 3.5, if we were to look at some sampling distributions, and even if we looked at multiple sampling distributions, my best guess would be, man, I bet the population mean is around 3.5 because look at my 3 sampling distributions that I calculated the centers for. The spread or the standard deviation, we noticed that it kept shrinking the more that we kept increasing our sample sizes. And that is a very common thing that'll happen. The bigger the sample size, the better, because it reduces our variation or our variability. Now, if you notice, this thing kept shrinking, and at first it went down by like 0.5 and then about another 0.5, but then it didn't go down by another 0.5, right? There's no way this thing's going to get to 0 in the end. So the main question here that you might have is there a formula that would help us determine what this specific standard deviation is depending on the sample size? And the answer is yes. We will talk about it soon in a future video. But the main idea I want you to get right now is that as you increase the sample size, the sampling distribution standard deviation starts to decrease and it gets smaller and smaller and smaller. And it will never be larger than what the true population standard deviation is. Okay, notice all of these standard deviations were always smaller than the populations. Now, with outliers, we kind of skipped over the O of our SOCs, but since our large sample sizes tend to average out extreme observations like rolling multiple ones or multiple sixes, then really sampling distributions don't have outliers. So that's another really nice thing about sampling distributions. We don't have to deal with these possibilities of extreme values that are going to throw off all of our data. And so that is all for video number